The next question that comes up a lot on exams is kind of a logic problem about disaccharides. Now, disaccharides are just two sugar rings connected to each other, so it's nothing particularly new, it's just you sometimes have to think a little more than the other questions. So in this example, this was from, I believe, your workshop this Wednesday, and you are told that X is a disaccharide, and you have to draw the structure of X. And then you were given 3 hints to help you figure that out. You are told 1, X is a reducing sugar, and remember that means that you have at least one anomeric OH available on one of those 2 rings of the disaccharide. You were told then that hydrolysis of X gives D-talose. Now remember, a disaccharide is 2 sugars, but when it's hydrolyzed, meaning the 2 sugars are split apart, all you get is D-talose. What that means is you have a disaccharide made of 2 separate D-taloses. And then C, X is a disaccharide with a beta-1,6 glycosidic linkage. Well, we'll get to that after we get a little closer to what we are supposed to look at. So first of all, let me pull up the structure of D-talose because I don't have it committed to memory. D-talose is 3 on the left, 1 on the right. So D-talose looks like this. One, two, three, four. 3 OHs on the left, and then the last one on the right. So this is what D-talose will look like. So your first job should be draw the Haworth projection of that D-talose. So we do that. We have our 6-membered ring. And then let's see, we have 3 on the left, and left means up, so 1, 2, 3, and then because it's D, this is on the right, that means this is up. Okay, so that is 1 D-talose. Now we have to draw the disaccharide that is made from 2 of them. And we are told that it is linked by a beta-1,6 glycosidic linkage. So let's start by defining what beta is. Remember, beta means that the anomeric OH and the CH2OH group are pointing in the same direction. So all that translates to, in one of the rings that I draw, this CH2OH group and the anomeric OH should be pointing up. Now notice it says 1,6 glycosidic linkage. That means carbon 1, which is typically your anomeric carbon, is part of the linkage that connects one ring to the other. So what 1,6 means is one of the 2 rings is connected by its carbon 1, and the other ring is connected by its carbon 6. So here is the carbon 1, the anomeric carbon of my first ring, and this needs to be connected to the carbon 6 of the other ring. So that means I'm going to draw the other ring now. Oxygen. So I should have like that. Okay? Now notice carbon 6 typically has an OH coming off of it. Carbon 1 typically has an OH coming off of it when it's separate. But when you have a disaccharide, wherever that glycosidic linkage is, one of those 2, basically those 2 carbons OHs kind of overlap on each other. It's not really what happens, but you can visualize it that way. Because if you were to hydrolyze this using H2O positive, you would end up getting OH and then OH. So all I'm doing is kind of saying, okay, if I'm putting these together, I'm going to erase one OH and connect that carbon to the other oxygen. And that's really what a glycosidic linkage is. Now, what else can we see about this? Well, that's really about it. Now I just have to make sure that all my OH groups are consistent with D-talose. So D-talose, we said before, carbons 1, 2, and 3 were all on the left, so that means they're pointing up. And now, what about this carbon over here, my anomeric OH? Well, we just need to make sure that anomeric OH is available because we are told in A, X is a reducing sugar. Okay? And so this anomeric OH is not part of the glycosidic linkage, which means it is available. Now, whether it's up or down, typically when they tell you about a beta or an alpha glycosidic linkage, they only focus on one of the 2 rings. So oftentimes you'll just see the other anomeric carbon drawn as a squiggly. But if you want to be 100% safe, you can just say, well, if I want everything to be beta, just make this point in the up direction too, because now this is a beta D-talose and this is a beta D-talose, and you're not going to be safer than that. There is one other way they could phrase statement C about the beta 1,6 glycosidic linkage. Now, this hint won't really tell you if it's alpha or beta, but it will tell you which carbons are part of the glycosidic linkage. Namely, if they tell you they took this disaccharide and they reacted it with CH3I, which we saw will take every single one of the available OHs and turn them into OCH3s, well, if they tell you they did this, and then they tell you 2 of the oxygens were found to not react after you hydrolyze. Namely, let's say I did CH3I, and so all of these OHs became OCH3. So this is OCH3, and this is OCH3, this is OCH3, and fast forward the video if you don't feel like watching me draw all of this. Almost done, and this becomes OCH3. And then you take this thing after it's been hydrolyzed, and you take this thing and then you hydrolyze it with H0 positive, well, you're just splitting the sugar rings apart, so you're breaking this bond here, and now this would become an OH, and this would become an OH, and don't forget, if an anomeric carbon is available in H0 positive, that will also become an OH, and now you are told following methylation or alkylation and then hydrolysis of your disaccharide, it was found that the OHs were found on carbons 1 and 6 of one D-talose and only carbon 1 of the second D-talose. What that means is this is the only OH in this ring, and these were both OHs in this ring. Well, what that tells you is one of those is probably the anomeric OH of your reducing sugar, but the other 2 were most likely part of that glycosidic linkage, because when they were part of the glycosidic linkage, they weren't OHs and couldn't react with CH3I. So that's another way they could give you a hint about where your glycosidic linkage is. They tell you 2 specific carbons did not react with CH3I or some kind of alkylation reaction. So they don't have to say CH3I, but they say alkylation, and that's what they mean. So alkylation. And that's the gist of most disaccharide questions. It's just a matter of figure out which base sugar it is. It'll almost always be an aldohexose, and they'll give you a list of them if it's necessary. And then it's just a matter of figuring out where was the glycosidic linkage, and was it beta, meaning both are pointing up or both are pointing down, so they're cis, or is it an alpha linkage where one would be pointing up and the other would be pointing down? And that's really the gist of it.